Hey everyone, so I'd like to get started. The first thing is that I heard from the AWS people that they started the process of getting things issued on the 26th, which is 3 days ago, so you should be getting it soon. For reference, I submitted the form about 7 days before that, so they're moving very slowly, but I think you should have AWS credits by the end of the week if you need them to run GPU machines or stuff like that. The moment you get AWS credits, or maybe even before you get AWS credits, I might suggest that you try to start a GPU machine, like a P2 machine or something like that, because sometimes you need to file for a limit increase to get a P2 machine, and that also takes a little bit of time. So I would suggest that you take a look at doing that. So you go to like, if you're using AWS, if you're not using AWS, it doesn't matter. But if you're using AWS, you can go to launch instance and try to launch a P2X large machine or something like that. So but yeah, anyway, hopefully that will be done soon. I'm sorry about the delay on this. They said it would take 7 days and it's taken almost twice that now. So my apologies. Any other things before we get started? Okay, I don't see any, so I'll go ahead with this. I have slightly fewer slides today, so I might go a little bit off the slides and talk about papers and stuff, or we might finish early, either way. So, but what I would like to talk about is combining multiple models. And this is really important and useful if you want to get like an extra few points of accuracy for anything, basically, because it's a pretty reliable way to get improvements. And there's a bunch of different kind of related but different topics that I'm going to talk about today. But anyway, the basic background is that we have many models that exist. And the reason why we have many models that exist is multiple fold. Number one, we could have different model architectures. And we could also have different initializations of those model architectures. So normally, if we do initialization, we will initialize our model architecture. Like, let's say we initialize the llama architecture. We start out with random 7B parameters, and then we train, and we get llama 7B for our pre-training, or llama 2 7B. We might initialize another model. This could be, the same architecture or different architecture, train it on the same data or different data, and get something like Mistral 7B. In this case, actually, maybe these are, I should have indicated that these are different architectures, but, we get a different pre-trained model. And of course, we could also make it bigger or smaller or whatever else, and then we get llama 2 7B over here. And then after we do that, there's a lot of fine tuning that goes on according to different strategies. So we have, llama 2 7B instruct, Vicuna 7B version 1.5, Mistral 7B instruct, News Hermes 2 Mistral 7B, or llama 2 70B instruct. So we have a variety of architectures, a variety of random initializations of those architectures, a variety of pre-trained models due to pre-training data or base models, and then a variety of fine-tuned models. And so we have this kind of like branching tree, basically. The reason why this is important is because when we're combining multiple models together, some of the methods are applicable to completely different models. Some of the methods are only applicable to models that share the same architecture. And some of them are only applicable to models that share the same initialization and training trajectory. And so I'll try to distinguish between those as we go forward. Cool. So the first thing I'll talk about is model ensembling. And ensembling is kind of a very general technique that you can use in a lot of different ways, but it has its disadvantages as well. So basically, ensembling is combining the predictions from multiple models. And the easiest way to do this, ignore the LSTM here. This is just any sequence modeling thing. It's because the slides are old. But like, let's say this is a transformer. It is calculating the current decoder state and you make a prediction. This is calculating a current decoder state and making a prediction. And based on some combination of the two predictions, you decide what you actually want to output at the next step. So why would we want to do this? Does anyone have any ideas why we'd want to use two models instead of using one model or just using the best model? Or maybe in what situations we would want to do this? Yeah. Uh-huh. Yeah, and what's the advantage of doing that? Yeah, it reduces the bias, kind of, yeah, sure. Mm-hmm. Yeah, so I'll repeat all of these. I think all of these are correct. So number one, it reduces the bias caused by a single model. Number two, it's kind of like a Bayesian perspective, which I'll talk about in a second. And then number three, we have different models and models are better at some things and worse at other things. So talking about the better at some things and worse at other things, the basic idea behind ensembling is that the errors that models make tend to not be consistent. Tend to not be as consistent as when the model is getting it correct. So we might have one model that says, like, let's say we just have really, really bad models. This is kind of a really obvious example. But we have like the dog barks and then runs and then dives or something like that. And we have one model that just had tons of stuff about diving in its training data, another model that had tons of stuff about running in its training data, or marathons or something in its training data. So we'll get model one, and model one will tend to give like a probability of like 0.3, maybe 0.4 and 0.05. And then we'll have another one over here that's like 0.32, 0.41, and 0.05 and 0.41 or something like this. And so when you average the two together, you tend to get the right answer more often because kind of the mistakes that they make tend to be less correlated than the probability of getting it correct. And of course, it's not perfect because ensemble models are not perfect, but this is a general tendency that we see a lot in models. It's because of this, it kind of smooths over the idiosyncrasies of the models. You can even just ensemble models from different checkpoints, and that still gives you improvements. And so when you ensemble models from different checkpoints, it's basically just what data did they see most recently, and that also smooths over, the fact that like this model happened to see some data more recently, and so it's less, it's biased towards doing that. So this is a pretty effective method. This is one of the few methods that I know is going to improve my accuracy almost every time. Like there's a bunch of methods that you can apply. And ensembling, it's very rare for me to ensemble two models together and not get a boost in accuracy in some way. So it's a good thing to know about. There's two main ways to combine models together, and both of them are useful in different situations. The first one is linear interpolation. And when you do linear interpolation, basically what you're doing is you're taking the weighted average of model probabilities. And the way that looks mathematically is like this. this is the probability according to the model M. So this is just, the probability of the next token according to model M. This is the probability of selecting model M. So you talked a little bit about the Bayesian approach to this. And this is basically saying, what is the probability that the parameters of model M are the ones that we want to be choosing in at this particular time step? And then we will calculate this. And so then you take the sum over this, and this gives you the next probability. For the second term, you can do this in two ways. The most common way to do this is just to have this be a constant. So you basically define mixture weights, which are like where the sum of the mixture weights is equal to 1, and this is always between 0 and 1. And so if you do this, then this is just constant. You can interpolate them together constantly. But you can also actually explicitly model this probability and say, oh, I'm currently in a situation where I really think model M will do a good job of predicting the probability. So I want to put most of my probability on model M. So you can actually learn this dynamically as well. And so if you have, this actually is rather practical and easy to do, because what you can do is you can just calculate the probability according to each model at each time step and train this model separately without loading these models into memory at the time of training this model. So yeah, this is something you can do as well. Any questions about this? Okay. Cool. So the other option is log linear interpolation. And so linear interpolation, you're taking a linear combination of the probabilities of each model. Log linear interpolation, you're combining together the log probabilities of each model and then renormalizing so that you get an actual probabilistic output. So basically what you do is you have this interpolation coefficient like I had before, but you're combining together the log probabilities. And so here we need to take the softmax. Thinking back here, I didn't take the softmax. Does anyone have an idea why I didn't take the softmax? Or why I didn't need to? Why I need to here? Yeah, so this probability is guaranteed to be 0, 0, and 1 and add up to 1. This probability is also guaranteed to be 0 and 1 and add up to 1. And then when you multiply those together, you can do a little bit of math and demonstrate that the resulting thing will be between 0 and 1 and add up to 1. That's not the case anymore when we start doing things in log space, because it's just not a linear function anymore. So you need to renormalize like this. Luckily, this is super easy. Like anything else you do in PyTorch, you just add things together and take a softmax, and you'll get an output. But you do need to do this, otherwise you're going to get something weird. The interpolation coefficient here also can be set to a constant, so you could learn it kind of dynamically, or it could be set to a constant. Cool. And these actually have different meaning. Oh, sorry, go ahead.
Have you touched on the dynamic learning thing?
Yeah. So basically, the way you would do this is you would have either the same model. You would either take representations from one of these language models, or you would take representations from another model, and you would just have a model that predicts what this interpolation coefficient would be. And the optimization objective for that interpolation coefficient is just maximizing the probability for next whatever data you throw. So this can also be good because this interpolation coefficient only, like, let's say you're interpolating two models together. It has one degree of freedom in each time step, right? Because you're only predicting a probability. If you have 5 models, you basically would be doing a softmax over five outputs, and that's a lot fewer. That's a lot fewer than the whole vocabulary, right? And so this is learning a good interpolation coefficient is relatively easy compared to learning what word to predict next. And because of this, you could actually tune this. You could tune this probability on a very small data set. And you could even have it be context independent. So you could just be, calculating literally five parameters here. And so because of that, like, let's say you have a special domain or a special task where you have like 50 training examples or something like that, or, 100 training examples. You can learn this interpolation coefficient very effectively on just a very small number of training examples. But like, it could be very useful because, like, let's say you have a special domain medical language model that's 1.3 billion parameters that you trained yourself, and then you have a 70 billion parameter language model that's like really good at modeling general English. So then you could learn the interpolation coefficient between those two such that the large general purpose language model will be generating all of the kind of grammatical stuff. But whenever you switch over to modeling technical terms from the medical domain, then it learns to upweight the medical language model or something. So this can be quite effective if you have a limited amount of data that you want to be fine-tuning those parameters. Any other questions about that? Yeah. Yeah, I'm just going to talk about that next. So linear versus log linear, you can actually think of this in logic. And what I mean by that is linear is kind of like a logical OR. It tries to come up with examples where either one of the two assigns a high probability. So we have the example of like bark, run, die. So if we take the average of these two in linear space, this would be 0.2. This would be 0.26. And this would be 0.21. And so a linear combination between the two will find run to be the highest scoring one, because on the left side, we have one model that really likes this output, and we have another model that doesn't. This can be good at using models that capture different traits, or it can also be useful if, like, for example, you have a small model that really captures like very specific vocabulary, and you want to upweight that specific vocabulary that gets a really low probability according to a general purpose model. This is also necessary when any model can assign 0 probabilities. So if you have like an example of vocabulary that isn't included in the like vocabulary of another model, or you have models with different vocabularies, it's necessary to do this. Log linear is more like logical AND. So the interpolated model only likes choices where all the models agree. And this is particularly good when you want to restrict possible answers. Like, you want to have one model be able to say, no, I really don't like this, so never output it. So for example, if you wanted to train a model that you knew was very adverse to toxic language and prevent the model from outputting toxic language, you could use log linear models. So I can't, unfortunately, calculate logs and exponents in my head well enough to decide this, but I'm sure that the linear model will pick the first one here, and the log linear model would pick the second one because the second one has a very low score here, so that would be downgraded by a lot more than that. Yeah. Yeah, so if yeah, and if there's any chance of assigning zero probability according to a language model, then really you can't even test that language model on that test set. So the issue becomes like, let's say you have two models with different vocabulary. If you have two models with different vocabulary, it becomes very tricky how to reconcile those two, but you could do linear interpolation between them, like match the output vocabularies that they do have, and then just not worry about the fact that the vocabularies are disjoint. And because one will assign a zero probability to those vocabulary items, but the other one is fine, so you can just do that. But if you're, in general, it will be very tricky to try to get two models with different vocabularies to play together nicely. So I would suggest thinking seriously about whether you need to do that or not before you start out. But yeah. Yes.
Are there any other types of interpolations that have other types of logical components, like the XOR or non?
You could definitely, so the question is, are there any other types of interpolation that have other types of logical components like XOR or NOR? You could definitely come up with one. I am struggling a little bit to think about when you would want to do that, but I'm sure you could, yeah.
I guess like is the inherent assumption that the errors are not correlated? Like what if they reduce the like
Yeah.
outputs of it?
So what if the errors are not, what if the errors are correlated? So think about what happens if the errors are perfectly correlated, which is when you're using the same model in two parts of the like ensemble. So you, literally, these model one and model two are the same model. If that's the case, nothing happens. It doesn't get worse. And so, of course, because this is machine learning, there's no guarantee, like, you know, unless we make some assumptions about the relationship between like the training set and the test set, or the model's errors in the test set, you can always do something that will make your accuracy worse. Like, let's say we flip the labels of a binary classification problem. No matter what you do, you're going to make your accuracy worse. But or no matter what, the normal thing you would do is it would make your, if it would improve accuracy normally, it would decrease your accuracy. But like under pretty reasonable assumptions, it's mostly going to be the case that errors are decorrelated to some extent. So yeah. And because of that, ensembling usually helps. Yeah.
The linear and non-linear stuff
About which one, which
the linear is the one for that pick one.
let me make sure I didn't mess it up on slides. Okay. So in my example, yeah. Go ahead. Sorry about that. Because this is where the average is higher, and then this is the one where. Thank you. Cool. Any other questions? Okay. So another thing I should point out is that we don't necessarily need to use models only as positive evidence. So if you're using log linear interpolation, actually your interpolation coefficients do not need to be positive. They can also be negative. And you can have things where you penalize the probabilities given by a particular model. And this has actually been used for a long time. It was actually used in machine translation since like 2005 or something like this. But the basic idea is that you have some models that serve as negative evidence. So you have kind of a core model. This might be your really strong general purpose language model. You have a positive model, which is the model that you want to kind of boost up and improve, and a negative model, which you want to decrease. And one example of this is in a paper that we did in 2019. The core was a machine translation model. And the negative model is an out-of-domain language model. And the positive model is an in-domain language model. And so the idea behind this is a machine translation model, you have to train it on machine translation data, and machine translation data is not very easy to get for particular domains, for example. You might only have machine translation data in the news domain, and you actually want to be doing translation in the medical domain or something. So what you do is you have your positive model here. This could be this is a machine translation model. This could be a news domain, or sorry, this could be a medical domain language model, and this could be a news domain language model. So you're subtracting out the news domain probabilities and adding in medical domain probabilities, moving in that direction. Another example of this is something called DXperts or DEXperts. And the idea here is you have a strong language model as your core. And then as negative, you have a weak toxic language model. So it was trained on lots of like bad text that you don't want to be generating. And the positive is a weak non-toxic language model that was trained on lots of like innocuous posts. So that would help you detoxify the outputs of the language model. So there's lots of examples of things like this that you can do too. Yeah. Yeah.
How does it claim of getting that?
So the positive in the machine translation example, this is a machine translation model where the input is like in English and output is in Japanese or something like that. This is only trained on Japanese, but it's trained on like medical Japanese, for example. If medicine is the domain we want. This is a language model that was trained on like news domain Japanese, or it could even literally just be trained on the target side of the machine translation. So it's trying to remove out the language modeling component from the machine translation. Cool. Okay. So another thing that I should point out, I didn't actually put it on the slides, is there's a lot of other ways to get multiple models. And I think a lot of people are probably familiar with dropout. It's a method for regularizing neural networks or deep learning models in general. And basically the idea is every once in a while, during training, you drop out some portion of the like nodes in the neural network model. And you can actually drop out. And normally what you do is at test time, then you just don't drop out anything and you use the whole neural network model. But another thing you can do is you can drop out at test time, drop out 5 times and combine those different models together through Ensembling. And that's actually something that people tried in the dropout paper. And this is one way to get multiple models. And actually, you can demonstrate that this helps. The original motivation behind dropout was precisely coming from this idea of ensembling. Another method that has been around for a very long time, it's another ensembling method, is bagging. And basically the way bagging works is you have a data set like this, and you just resample the data set. So you sample all of the output with replacement, and you get another data set of equal size, and then you train on this. But you do that like 10 times and you train 10 different models and then you ensemble those models together. And so this is another way to get multiple models. And both of these still improve your robustness because they basically get a different view on the data. So they smooth over some of the idiosyncrasies. And as I mentioned before, you can also get multiple models from different checkpoints and then put them together. And all of these methods are pretty related. Both of them, basically what they're doing is they're taking advantage of the fact that you have particular models that saw different data or saw data in a different order, or different nodes saw different parts of the data because you dropped out some of the nodes when they were backpropping on particular varieties of the data. So even things like this can give you models that are different enough that to help when you're ensembling or combining them together. And then, of course, you can also combine together like very different models like this, and that also works in different ways. Cool. Part of the reason why I wanted to mention that dropout, though, in particular, is there's also other efficient methods for using multiple models. So the big problem with ensembling is the cost. And simple ensembling is very expensive because it requires you to run multiple models at test time, at inference time. And this is something you don't want to be doing if you're, deploying a service or something, because it like linearly increases your cost by the amount of models that you're running. And it requires both n times the computation and n times the memory. And memory is actually probably the worst thing because you need to deploy extra GPU machines and other stuff like that. So the question is there any way we can get some of the benefits of ensembling without having to create multiple models? And luckily the answer is yes. The easiest method for doing so is something called parameter averaging. And basically what you do is you just average the parameters of multiple models together. This only works under certain conditions. So does anyone know what these conditions might be? There's a few obvious ones and maybe a few slightly less obvious ones. So like first question, do you think you could average together the parameters of llama 7b and llama 70b? No? The answer is no, but why not? I mean, what does that even mean in the first place, right? Like they have totally different numbers of parameters. You wouldn't be able to find a one-to-one association between 7b and like 7 billion parameters and 70 billion parameters. What about averaging together, let's say llama 7b and Mistral 7b? Yes, no? Yep.
I'm guessing that like for the different architectures, the parameters could mean different things. So if you average them,
yeah, for different architectures, the parameters could mean different things. And even if the architecture is exactly the same, even if your random initialization is different, then that would be disastrous, because basically in neural networks, there's no inherent meaning to like parameter number one, right? And there's the idea of permutation invariance, which is you could like randomly swap all of the dimensions between it within a neural network and get exactly the same function, as long as kind of in layer number one you swap, and then also take the inputs in the next layer also swap. So as long as if you have a weight matrix that results in the outputs being ordered like 1, 2, 3, 4, 5, 1, or 2, 1, 3, 5, 4. As long as you also swap the input input dimensions of this weight matrix, you get exactly the same thing. Because they're linear combinations of the parameters together. So neural networks have this feature of permutation and variance. So models that were trained from like different initializations won't be able to be combined together in this way. But the good thing is actually we have a whole bunch of models that come from the same pre-trained model, right? So we have this initialization here. This initialization was used to train Llama 2 7B, but now we have like hundreds of models that are derived from Llama 2. We have hundreds of models that are derived from Mixtral. And there, all of the dimensions actually mean the same thing because they're derived from the same parameters in the first place. So those ones we can average together. And there's basically two ways that we can do this. One is by averaging together multiple checkpoints during training. So originally, this was the big thing that people did. Like you would train a model from scratch for a really long time, but then you would take the final 5 checkpoints and you would just average them together. And this helps reduce some of the noise that you get from stochastic gradient descent and can improve your overall accuracy. If you're fine-tuning any models, this is something you can do also, because you're probably going to be saving checkpoints. You can just take the best 5 checkpoints and average them together, and that actually can improve your accuracy quite a bit. Another thing is fine-tuned model merging. So fine-tune in several ways and then merge them together. And so, for example, we might take Llama 2 7B instruct and Vicuna 7B 1.5 and merge them together with some weights. And we could, smooth over their idiosyncrasies and get better results too. Cool. Any questions here? Okay. Oh, yeah.
So would it be possible to, I'm training on this model and I want it to be non-toxic. So I just train another like just by like non-toxic data set. So I know that I use checkpoint across like those different trainings and I just do general averaging.
Yep.
Would that be like so I would say like it's pretty efficient just because it's training from the same model. So you get to keep those checkpoints and at the end of time you just basically
Yeah, so would this parameter averaging be a good method for making a model less toxic, for example? The answer is a little bit trickier there, I guess, because I feel like this is good for mixing 2 models together. So if you're mixing your like non-toxicity tuned model or your safety tuned model with the original base model that was not safety tuned or something like that, then you might get something in the middle. So you might get something that's less safe than the model that was tuned to not be toxic. So it might be, yeah, I'm not sure, but like let's say you have a model that somebody else did like a really good job instruction tuning for you. And anytime you start using safety tuning on it, you like hurt the instruction tuning, like the model gets worse. I could see a world where you take the base model, the same base model, you take Llama 2 7B, you train like a less toxic version of Llama 2 7B and then do parameter averaging with the like well instruction tuned model. That might work. That might make something that's more safe and like not much worse instruction tuning. So there's definitely, I think, creative things that you can do for that. Maybe I'll go in directly into the methods. There's a few recent papers on this. Like this method has been around for a long time, since at least 1996, but recently people have examined it a lot in the context of kind of modern networks. And this paper, Model Soup, examines 2 strategies. The first one is uniform averaging, where you just average all the parameters together, like as you would expect. But they also have a greedy averaging method. And basically what they do here is they add one model and check if the whole like averaged model improves. And then only if the whole averaged model improves do they keep that model. Otherwise, they throw it out and then they don't use it. So what they demonstrate, this is a little bit small, but basically the purple star here is when they use greedy averaging, and then the blue circle here is when they use the uniform averaging, and then green is all of the models that they put into this average. And what they found is this is average accuracy on ImageNet, which is the thing that they used in deciding which models to merge in greedily. And then this is on distribution shifts. So this is on other data sets other than the ones they use specifically for training. And what you can see is the greedy averaging method does better than the best single model on the data set that they used to decide that greedy average. The uniform average actually does worse than the best model. So you would actually be better off for ImageNet accuracy to just use the best model, but it's more robust. So on the distribution shift, like data set, it actually does better than any of the models. So you can see that there's kind of trade-offs between choosing those essentially. Whoops, that's a typo. That should be ensembling. But they also demonstrate that averaging is correlated with ensembling. So this is the image net accuracy of the parameter average model. This is the image net accuracy of the ensemble. So this is actually, I think, a really interesting figure. What it shows is that there's a pretty strong correlation between the two. Averaging is almost never better than ensembling the two together, but it's faster, of course. So it's better because it's faster. And there are situations where the ensemble is much better than the average model. So like the average model hurts, the averaging hurts, ensembling does not hurt. So what this shows you is parameter averaging is safe and it nearly approximates model ensembling most of the time, but there are cases where it doesn't. So you do need to be a little bit careful and it might hurt your accuracy in some cases. Yeah. Oh, yeah, sorry, very good point. Yes, it's pairwise. Yeah.
So in this case, where primary invariant so like the primary actually output to not be able to do the same as ensembling itself. How do you know if it's gonna be the case for your particular path?
Yeah, so notably, all of these are initialized. It's been a little while since I read this, but I know all of these were initialized from a model that was already pretty good on ImageNet, and then they were fine-tuned in different ways, I guess. And so this, I think this might be initialized with a model that was trained on a different data set or something like that. And so they are all starting from the same initialization. So parameter permutation invariance is not an issue there because they're starting from the pretrained form. But despite the fact that it's not a problem, there are cases where like averaging is detrimental compared to ensembling. Cool. Okay. So yeah. Yep. Yep. Okay. Yep.
And that form then it is possibility that from the original
Mm-hmm.
and whether it comes to other things or it comes to other things that people like would actually be differently. So I was sure that like the human side, like even like randomly inspired by random and slightly different parameters, it could be like using like someone relatively similar.
Yeah, so that's a great question. I'll just repeat it, which is these experiments were done on CNNs or ImageNet, like CNN-based ImageNet classifiers. Is there something different than transformers, particularly because transformer representations tend to be like very concentrated in particular parts of the space? That's an excellent question. What I do know is a lot of people do merge together transformer models. In fact, if you look at the Hugging Face leaderboard, there's like something and something merged together like all over the leaderboard, and it does tend to improve accuracy. So I know it is definitely effective for transformers. However, are there specific model like parameter averaging or model merging methods that could improve accuracy by taking advantage of the fact that transformers behave in a certain way? I think that's totally possible, and it'd be an interesting research direction. I'm not familiar enough with that particular part myself to say, oh, I have this great idea that you should work on, but I think if you're interested in it, you could definitely do it. Yeah. Cool. Anything else? Okay. So there's also the idea of task vectors. And basically task vectors, here we are just merging together two models by taking the parameters of the models and averaging them together. Task vectors and other related works specifically take advantage of the fact that we're looking at different fine-tuned models. And so these are models where we have a base model and we know that that we fine-tuned from this base model. And the basic idea is that we have our base model here, and the task vector is the difference between the base model's vector parameters and the fine-tuned model's parameters. So that's what they define as a task vector. What does this allow us to do? This allows us to do a number of interesting things. The first one is that we can actually subtract out quote unquote tasks that we don't want. So like, let's say we had a model that was trained on lots of toxic text, or we had a model that was trained on lots of private text or something like that. We could actually subtract out the task vector from this and basically attempt to remove the model's ability to do that sort of things. You can also take two task vectors and combine them together and like get the model from the combination of the two. This isn't exactly the same as averaging the parameters, because if you average the parameters, you would probably get something in the middle right here. But if you average the two vectors or add the two vectors together, you would get something over here. Actually, sorry, if you average the vectors, maybe it's the same. So you could like add together the two vectors, and that would be something different than taking the average. So it gives you a little bit more flexibility about things to do. And another thing this allows you to do is this allows you to try to resolve conflicts between vectors of different tasks. And so this is an illustration of this method here. And this has three tasks. Basically, it has model 1, model 2, model 3. And each of them has vectors. And you'll see that in some cases, these vectors conflict. So we have like pink going up, we have yellow and purple going down, we have yellow going up, we have pink and purple going down, et cetera, et cetera. And what this does is this identifies the vectors that are pointing the most strongly in particular directions. And then it resolves conflicts between them and comes up with a vector that tries to move in a direction that improves all of the tasks at the same time. And they demonstrate that this is the better method for kind of improving the ability to do all of the tasks compared to just averaging things together. So, yeah.
In the first example, you talked about like the negative direction.
Yep.
Does it also work in the, like if you just add more in the direction of the task vector, does it make it better?
Yeah, so this is yeah, you could move it more in that direction. There's obviously no guarantee that it would make it better, but it might make it more extreme at least. So yeah. Any other questions? Yeah. Mhm.
Even with one gradient different, if we end up in that.
Yeah.
So, it's like any discussion in
Yeah, so this is a great question. I can explain a little bit. I'm not going to talk about meta learning extensively in this class, but just to give a very quick primer for people who don't know about it. This is an example of a paper on meta learning for low resource machine translation. You can take a look at this paper or not take a look at this paper. But the reason why I wanted to look at this paper is because it has a good illustration of what meta learning is. And basically, if we are doing transfer learning from a single task, what we do is we have like a Spanish English machine translation system, and then we fine tune it to try to hit to try to be a good Romanian English or Latvian English system. If we're doing multitask learning, which also could be equivalent to like instruction tuning, for example, we have French, Spanish, and Portuguese. We train on all of these, and then we fine tune to be a good Romanian translator, or Latvian translator. Whereas meta learning, what it's trying to do is it's trying to learn a good initialization that makes it easy to fine tune, to try to come up with a model that is good for fine tuning into new tasks. The way you do this is basically you have two steps of gradient descent. And so you have a first step where you train the model, where you have an update on like data from French, for example. And then you have another update where you train on like Latvian or something like this. And this is a very informal description. There's a lot of stuff we could talk about here. I could have a whole class on this, but we're not gonna, I don't have one planned at the moment. And so you update once and then you update again and you differentiate through this update process so that this becomes like essentially a good initialization for training on other languages or for other tasks or things like that. Now, going back to the original question is there a connection between meta learning and these task vectors? I'm not 100% sure about that because I think these test vectors are generally created post hoc, and so they're not like there's no explicit learning step to try to make them generalize well. One thing that maybe might be interesting to people, this is a paper that we like literally just put on archive about last week. And we didn't actually use meta learning in this paper just because meta learning actually is hard to implement because you need to do this kind of double differentiation and it can become very, very expensive for large models. But we did something a little bit motivated by meta learning. And what we did is we took a pre-trained LM And normally what you do is something like continued pre-training on new documents to learn knowledge from the new documents, or maybe instruction tuning, including instruction tuning on data on documents about the kind of data that you would want to be answering questions about. So like, let's say you're trying to train a medical language model, you might train on lots of medical documents. But what we did here is we had a step where we trained in advance to get on question answer pairs and documents from another domain. And then we have a step after that where we train on documents from the domain we want to answer on. So like we might train on Wikipedia question answer pairs and Wikipedia documents. And then in the second step, we would train on medical documents. And we demonstrate that basically this allows the model to do a better job of question answering over these documents that we fine tune on over here. And so kind of going back to the meta learning paper that I talked about before, the meta learning paper tries to get the parameters in a good space so that after you fine tune on another data set, you do a good job of that. In this paper, our motivation is that the model kind of learns that when you train on documents, you should be able to answer questions about those documents. And so when you get a new set of documents, it's kind of in a good part of the parameter space to make that easy to do. So if meta learning is interesting, there are tutorials on meta learning that I could probably share. And then if you're interested in kind of like learning knowledge from continued pre-training or something like that, you can take a look at this paper as well. Cool. Any questions about that or? Okay, cool. I'll jump on to the next. So anyway, I talked about several methods for merging models together. There's a popular toolkit called MergeKit that makes it relatively easy to do this. It implements a lot of the models that I talked about here, including the linear methods, the task arithmetic method, and ties. So I talked about these. DARE is kind of like a expansion on this. So if you want to merge together models, it's relatively easy to do from a software standpoint as well. So you can take a look at that. Another really simple thing is distilling ensembles. And so we already talked about distillation. The idea is simple. So parameter averaging only really works for models within the same run, same model architecture, same initialization. So knowledge distillation trains a model to copy the ensemble. And so it tries to match the distribution over the predicted words for an ensemble. And so this allows the model to make the same, good predictions as the ensemble, make the same bad predictions as the ensemble. It just allows you to learn more efficiently, just like distillation does in general. And actually, model distillation, the original motivation for it when Jeff Hinton proposed it in 2015 in this paper was to copy an ensemble. Now we use it for a lot of other things, like in the distillation, like we talked about in the distillation class, but this was the original motivation for that. Cool. Next, I'll move on to sparse mixture of experts models. And this is really important. This is used in a lot of modern models. It's allegedly used in GPT-4. And it is definitely used in Mixtral, which is kind of one of the state-of-the-art open models. So I think it's a good thing to know about. What these do is they take advantage of sparse computation. So if you think about what happens when you do a scalar tensor multiply, where the scalar is 0. And basically the result of the entire resulting tensor is guaranteed to be 0. And so you don't even need to do the computation. You don't need to even bother. And so this manifests itself in a bunch of different places in modern models. The first one could be single rows in a matrix multiply. So if you have a big matrix multiply like this, or matrix vector multiply like this, and some of the rows are 0, then that's one place where it happens. You can also do this between 0 and not just rows, but also larger tensors. And you can even do it in whole models in an ensemble. So the first one, this can be optimized automatically by GPU. The second one, this often occurs in sparse mixture of experts models. And the final one, basically, you just don't need to even use the model in the ensemble. So if you somehow optimize an ensemble and it turns out that the probability of one of the models is 0, you just can throw it out and not use it at all. So GPU level sparsity support. NVIDIA GPUs support a bunch of different types of sparsity. And the wonderful people at NVIDIA have worked hard to make the support work to some extent anyway. And there's a library called cuSparse, and this is used in PyTorch and all these other things as well. And just to give an example, a vector matrix multiply with a sparse vector, such as one that comes from a ReLU activation, basically what happens is, let's say you only have 3 parts of this vector that are active. You actually just don't need to calculate any of the columns here. So that makes your life relatively easy. But the specific thing that I wanted to talk about is the sparsely gated mixture of experts layer, because this is what is used in Mixtral and probably the GPT models as well. And what you do is you have a feed-forward network. And normally a feed-forward network in a transformer is this like really wide thing. It's this huge wide feed-forward network that you use to extract a whole bunch of features at each layer, and that's where a lot of the computation in transformer happens. And what sparsely gated mixture of experts layers do is they first have this gating network here where it calculates mixture probability, but the mixture probability is 0 for many or most of the parts of this feed-forward network. And so for the ones where it's 0, you just don't calculate it. And then when you mix them together, you use the mixture rates. And this is actually really simple. It's like several lines of PyTorch code, maybe like 7 or 8 lines of PyTorch code. But the basic idea here is you have this gating function where you calculate the gating function based on the input. And then you have this keep top k operation. And then you take the softmax over this. And the keep top k operation is if the value is within the top k, you just keep it. And if it's not in the top k, you don't keep it. So that's all basically. But what's great about this is then you don't have to calculate like many of them. And so for example, if you keep the top 2 out of 8, you reduce your computation by 4 times for this part. So any questions here? Yeah. Sorry, what exactly do you mean by easy to parallelize? Are you talking about like a GPU can calculate lots of things at the same time? Yeah, so I think if you have a very small model, you're actually not going to get as much from this because you're essentially not bound by computation. Like you're bound more by memory movement and the GPU and other stuff like that. But once you start getting up to the bigger models, you actually are bound by computation. So reducing your computation by 4 actually is a big one. So it's a really good question. Any other questions? Yeah.
Like what exactly?
So this will probably be just Oh, sorry, I don't have this on here, but this will be often a linear layer followed by a softmax. Or actually, no, it doesn't even need to be followed by softmax. It could just be a linear layer. And I think actually, I didn't put it on this slide, but I have in the references on the website, I have the actual implementation in Mixtral. You can go in and look at it. It's really simple. One thing I didn't put on here, which actually relates to the question before, is hardware-wise, this implementation is tricky if you do batching. And the reason why it's tricky if you do batching is because different experts will be active for different like parts of the batch. So if you do that, you need to do some tricky stuff. There's this. Like so much of AI research nowadays, the best resource for this is social media. So this is, there's a kind of interesting discussion of this. If you search for like GPT fast Mixtral on Twitter, it talks about this. But basically, there's a bunch of little things you need to pay attention to, and ways that you can do tricks to make this work fast on GPU, which also kind of addresses the concern. So you can look for Horace Ho's discussion of this. So. Cool. So the final thing I'd like to talk about in the last 10 minutes is pipeline systems. And pipeline systems are systems where we have models that basically the output of one model becomes the input of another model. And to give an example of this, a cascaded system is basically a system like this, where you take the output of one system and then you feed it into the input of another system. So a very stereotypical example of this is speech translation, where you run speech and then you do speech recognition into text, and then text you do machine translation into another language. And one of the frustrating things about speech translation is these systems are stubbornly better for a long time than many systems that try to do end-to-end, like speech to text in another language. There's a couple reasons for this. Does anyone have an idea what one of those reasons might be? Yeah.
The data that points on
Exactly. So data availability is way better for speech to text in the same language and text to text in another language than it is for speech to text in another language, because there just aren't large data sets that have speech and text in many languages. So there's a bunch of tricks that you can do to, fix this, but still it's tricky. And there's a couple other reasons. Another reason is like actually speech to text in the same language is just a much more straightforward task. And so it's a bit easier to learn. Another thing is interpretability. And the reason why interpretability is important is basically like, if I'm talking to you in a different language, like you speak a different language, I'm talking to you through a speech translation system. I actually want to know if the speech recognition worked, because I know if the speech recognition didn't work, then I'm pretty sure that the translation didn't work either, right? And I can verify the speech recognition, but I can't verify the translation. So there's other reasons why you might want a cascade system other than just like accuracy or other things like that, but this is a thing we definitely do. There's another idea of stacking, and stacking is very similar to cascading, but it allows you to take two different models for the same task, but with predictions in different ways. So just taking another example, actually, maybe ignore the example I have here, but we could just take the example of speech translation. The speech translation model we would first do speech recognition into, like, let's say English. And then we would do translation, and the input to the translation model would be speech in English, text in English, and we would generate the output in Japanese. So it would take both the speech and the text when it was doing translation. And that would allow it to, number one, basically get a second opinion about whether the transcription was correct. But also, like, let's say there was some unique information that only appeared in the speech. So just to give an example, I read the book, I read the book, are both transcribed exactly the same way. And they're different translations, obviously, because one is, present or present tense, and the other is past tense. So there are examples where adding a cascaded system would lose information and a stacked system would not. Another thing is iterative refinement. I think this is actually really interesting because large language models have opened up a whole bunch of possibilities for us in this space. This is like cascading and stacking, but it can be done multiple times, and it can be done multiple times with the same model. So we have an input, we feed it into the model, we get an output, and then we feed the output back in and gradually refine it and make it better and better. And the first time this was done in neural networks was through something called deliberation networks. And basically deliberation networks, what they do is they take in an output and then they just gradually refine it to make it better and better. They used a reinforcement learning algorithm to do this, where you generated the output and then improved it. Another thing that's really popular nowadays is diffusion models, and I haven't quite decided whether I'll have time to cover diffusion models in depth, but basically the way a diffusion model works is very similar. You start out with nothing, and then you gradually make it better and better. The key difference between deliberation networks and diffusion models is diffusion models you can train from scratch by basically noising the input, applying noise to the input. In training very efficiently. And these are very widely used in image generation. They're not super widely used in text just because regular autoregressive models are so good for text. But there are a few efforts to do that. And then a final one is self-refine. And the idea behind self-refine is you, actually, maybe I can open the paper because the paper has a good figure. Actually, I thought it had a good figure. Yeah, so maybe this is a figure. So basically, what you do is you feed in the input, you generate an output, and then you ask the model to give you feedback on the output and say, yes, this output is good, or like, let's say you're doing code generation, it can say, no, this output has an error in it. This is a problem with your output. And then you feed in both the output and the feedback and ask the model to refine its output. And you do this over and over again. And this allows you to improve the output. And this has ended up being pretty effective in a pretty wide number of tasks. One caveat about this is your model has to be really good for this to work. So only models kind of on the level of GPT-4, not on the level of GPT 3.5, have the ability to do this pretty consistently. So it is something you need to be aware of. Cool. Yep, that's all I had for today. I'm happy to talk about it. Yep. Yep, this is a great question. So if stacking has the potential to address information loss, why would we ever choose a cascade model? I think basically there's potentially two reasons. One reason is data availability. So in order to train a stacked model, you obviously need the outputs. I guess you could, yeah, I guess you could run the and generate outputs for every training example you have. But you would need to do that. So you would need to run speech recognition for every example. And you also couldn't use any examples where you don't have the original input. So you couldn't use text to text examples unless you like synthesize speech from text for machine translation, for example. So makes it a little bit more tricky due to the data requirements, but that's not insurmountable. The second reason is complexity and efficiency. So, you do have to come up with a model that takes in speech and text and runs that, and it might be easier just to hook together a speech recognition model with a translation model. So, but like, I think overall, I like these methods. I think these are good methods to use. If you're thinking about using a cascade system, you should definitely consider using a stack system instead. So, yeah. Yep. Can you measure the contribution of each component to an ensemble? The very, very easy way to do that is look at the interpolation coefficients if you train the interpolation coefficients. Otherwise, I guess it depends on what you mean by each contribution, but looking at the interpolation coefficients is a pretty good way to do it. Yeah. Also, just how much did the accuracy improve? Is iterative refinement the same idea as boosting in traditional like machine learning systems? I think it's a little bit different because iterative refinement, what I'm talking about here, it's usually taking in the output, like rather complex output of a system and modifying it. So you're not just modifying the probabilities of like a single classifier, you're modifying the actual outputs that were generated. And from the point of view of a boosting model over a single categorical output, it might actually be similar or the same. But this is more like you generated a textual output and then you feed in the textual output to the other model and refine it, like generate a new textual output. So I feel like it's a lot more complex. Cool. Okay, thanks a lot, everyone.